So imagine asking an AI assistant to order your favorite groceries. Like, you've done this 100 times.
Yeah, it knows the exact brand of coffee you want.
Right. It knows your address, your payment info, all of it. But today, you make the request, and the AI just, it completely freezes.
Just stops working entirely.
Exactly. And all because the grocery store updated the layout of their homepage overnight. Like maybe the cart icon moved 2 inches to the left, or it changed from a shopping basket to, a little tote bag.
Right, a tiny visual tweak.
Yeah, and suddenly your highly advanced AI is just completely paralyzed.
It's a really common experience right now, unfortunately. And honestly, it exposes the hidden reality of most artificial intelligence deployed on the web today.
It's a lot more fragile than people think.
Oh, absolutely. I mean, we see these incredibly flashy demos in, highly controlled environments, but beneath the surface, these systems are remarkably fragile the second they hit the real, messy, constantly shifting architecture of the actual internet.
And that fragility is exactly what we're tackling today on this deep dive.
Yeah, it's a huge problem to solve.
We are looking at a groundbreaking new state-of-the-art paper-driving generative AI architecture. It's titled Learning to Adapt, Self-Improving Web Agent via Cognitive-Aware Exploration.
Quite the title.
It is, yeah. But our mission for this deep dive is to basically uncover how AI is finally breaking free from rigid, human-coded scripts. We're going to explore a framework where an AI learns to autonomously browse the dynamic internet by actively hunting down its own limitations.
It's essentially learning what it doesn't know.
Exactly. So to really grasp why this paper represents such a massive paradigm shift, I guess we have to understand the fundamental architecture of why that grocery assistant froze in the first place, right?
Right. So the current generation of multimodal large language model web agents, what we often call MLLMs,
Right.
they are essentially passive. They rely heavily on manually crafted execution pipelines. You'll often hear about prompting frameworks like React or Tree of Thought.
Wait, I actually want to clarify something there because I feel like it's easy to misunderstand those terms.
Sure.
React and Tree of Thought, they aren't hard-coded UI scripts, right?
Yeah.
Like a human engineer didn't sit there and type click X, then click Y.
Oh, no, that's an important distinction. They are prompting frameworks. We are essentially giving the AI a mental checklist. So React, for example, stands for reason and act. You prompt the AI with a strict sequence. You tell it, first, think about what you see on the screen. Second, take an action based on that thought. Third, observe the result.
Sounds logical enough.
It is, but the problem is, if the AI expects to see a standard checkout button based on its training, and the store has replaced it with some vague icon, the observation doesn't match the prompt's premise at all.
So it just breaks.
Completely. The AI's reasoning loop just collapses because it encounters something outside its static training data.
So it's looking for a very specific anchor in reality, and when reality changes, it is no fallback plan whatsoever.
Exactly.
But researchers have tried to fix this by throwing massive amounts of human data at it, haven't they? Like, I'm thinking of data sets like Mind2Web or OS World.
They have, yeah. To build those data sets, research labs essentially pay human workers to just sit at computers and click through thousands of websites.
Sounds tedious.
Oh, incredibly. But the software records the exact X and Y coordinates of their mouse clicks, their keystrokes, and the underlying code of the website at that exact millisecond.
Wow.
And then the AI is trained to mimic those incredibly specific human pathways.
Okay, but the real-world web is so chaotic. It changes literally daily. I mean, A/B testing means two users might not even see the same homepage at the exact same time.
Right, the data gets stale immediately.
Yeah. It's like giving a tourist a highly detailed printed guidebook from, like, 2010. The instructions are flawless for the world as it existed back then. But the second a road is closed for construction or, a restaurant changes its sign, the tourist just loses their ability to navigate.
They're completely lost.
They just stand there frozen on the sidewalk because their guidebook doesn't have a contingency plan for a detour.
A tourist without the ability to ask for directions or figure out a new route on the fly. And historically, the tech industry's instinct has been to just print a newer, bigger guidebook. Just throw more human data at the problem.
Just hire more people to click things.
Right. But the authors of this paper realize that human trajectories are just too scarce and incredibly expensive to produce at the scale of the entire internet. You cannot hire enough humans to click on every single variation of every single website every single day.
It's impossible. So the fundamental problem isn't a lack of data. It's a lack of self-awareness.
Yes, perfectly stated. These passive agents do not understand their own cognitive boundaries.
Cognitive boundaries.
That is a crucial term introduced in the paper. A cognitive boundary is basically the mathematical limit of what the AI actually comprehends with high confidence.
Okay.
When it steps outside that boundary, it doesn't realize it's lost. It just hallucinates an action and fails. The AI needs a mechanism to evaluate its own boundaries dynamically, like in real time.
And this brings us to the actual solution presented in the paper. It's a framework called SCALE, S-C-A-L-E, which stands for Self-Cognitive Aware Learning and Exploration.
That's the one.
And the most surprising element of this to me was that SCALE doesn't use multiple different models working together.
No, it doesn't.
It takes a single AI model and essentially splits it into 3 distinct adversarial roles that argue with each other to find the truth.
Right, an internal debate.
Yeah, the selector, the predictor, and the judger.
It is a brilliant architectural choice. But before we get into the internal debate between those 3 roles, we have to talk about how this system actually perceives the web, because it fundamentally changes the equation.
Okay, let's get into it.
Instead of relying on hidden HTML code or accessibility trees, Scale uses something called set of mark, or SOM, visual processing.
Let's pause there for a second because a lot of previous models loved looking at the raw code of the website, right? Like the document object model or DOM tree to figure out what to do. Why the shift to purely visual processing?
There are 2 major reasons for that. First, the DOM is basically the hidden scaffolding of a website, the code that tells your browser where to put text and images. But modern websites are built dynamically.
Right.
An interactive button might not even exist in the DOM until your mouse literally hovers over a specific area. Furthermore, the real internet is hostile to bots.
Oh yeah, constantly getting blocked.
Exactly. Websites constantly use services like Cloudflare to block access to their underlying code to prevent scraping. If your AI needs to read the DOM to navigate, it will get blocked constantly.
That makes sense. And the second reason?
Well, humans don't read HTML to buy groceries.
Oh, right.
We look at the actual pixels on the screen. Scale looks at a GUI image, basically a literal screenshot of the website.
Okay, I see.
The set of mark process overlays little visual markers, like brightly colored bounding boxes with numbers inside them, over every interactive element on the screen, so it translates a visual layout into a numbered map.
Okay, but wait. Running 3 distinct AI personalities, evaluating every single visual change on a screen, doesn't that require a massive amount of compute?
It does take some power, yeah.
Like processing an image, drawing bounding boxes, running an internal debate, generating a hypothesis. Isn't that incredibly slow compared to just scanning a text file of HTML code?
It's a fantastic point, and it really touches on a major debate in AI right now, which is inference time compute versus training time compute.
Right.
Yes, during this exploration phase, running visual processing and adversarial internal loops is computationally heavier and slower upfront, but the trade-off is universal robustness.
Meaning it won't break as easily.
Exactly. A website can change its hidden code 1,000 times, but if the buy button still looks like a buy button, the visual agent can still click it. If you want an agent to act like a human, it needs to see like one, regardless of the initial compute cost.
That makes a lot of sense. It interacts with the visual layer, the exact same layer you and I interact with. So we have this visually marked up screenshot. How do these 3 distinct personalities, the selector, the predictor, and the judger, how do they actually operate?
So it operates in a continuous loop of self-confrontation. First, you have the selector. The selector's job is to look at the visual interface and proactively hunt for things the AI might not understand.
It's looking for trouble.
Right. It calculates an uncertainty score for the elements on the screen and deliberately seeks out the agent's blind spots. For instance, instead of clicking a standard high-confidence buy button, the selector might target a weird unlabeled icon hidden in the footer of the page.
Okay, so it wants to find the edge of its own map.
Exactly. Then the predictor steps in. The predictor represents the agent's current understanding of the world. It looks at the selector's chosen action and tries to guess what the outcome will be.
Like forming a hypothesis.
Right. And crucially, it has to explain its reasoning based on its existing mathematical weights.
So the selector's like a mischievous scientist actively trying to break the system and find anomalies.
Yeah, that's a good way to put it.
And the predictor is like an overconfident intern saying, oh, I have a hypothesis. I know exactly what will happen when we click that. And then the action is actually executed on the real website.
Right. And that is when the third role, the judger, takes the stage. The judger looks at the predictor's initial guess and then looks at the new visual screenshot of what actually happened after the click.
The moment of truth.
It objectively compares the two to verify if the predictor was correct. The judger is the cold, hard reality of the experiment's result, holding the clipboard and saying whether the intern's hypothesis held up.
I want to make this really concrete for you listening, because the paper gives a fantastic specific example of this exact dynamic occurring.
Oh, the shopping one.
Yeah, picture a typical shopping website. The AI is browsing around. It already knows that clicking a picture of a product will take it to that product's detail page.
Right, that's standard.
The predictor knows this. The judger confirms it. It's safe, high-confidence territory. But then the selector spots a button labeled Advanced Search. The AI's internal confidence about that specific button is low, so the selector chooses to click it.
And then the predictor makes its hypothesis. It guesses that clicking Advanced Search will simply refilter the products currently visible on the page. It assumes it's just a local sorting tool, like arranging by price.
So the click happens in the real environment. And it turns out the predictor is dead wrong. Clicking Advanced Search doesn't just refilter the current page. It pops open an entirely new, complex overlay menu with a dozen different search parameters, sliders, and checkboxes.
And the judger immediately flags this as a failure. The prediction completely failed to match reality.
This is a pivotal moment in the framework, isn't it? Because normally, in software design, a failure is a problem to be avoided. Like if your AI fails, you don't get your groceries.
Right. Usually failure is bad.
But in the context of Scale's exploration phase, failure is the entire objective.
It is, because that failure is the exact moment the AI discovers a cognitive boundary. It has successfully located a gap in its own knowledge base.
If it only ever clicked things it already understood, it would never learn anything new.
Exactly. By actively hunting for where it guesses wrong, it generates highly valuable, completely novel training data.
But how does the AI actually learn from this? Is it just keeping a temporary note in its short-term memory, or is something deeper happening? Because if it just remembers it for the current session, it's going to forget as soon as it restarts, right?
That is a crucial distinction. It's not just holding this in its immediate context window. The judger takes this failure and formats it into a highly structured question and answer pair.
Oh, interesting.
Yeah, the data essentially says, question, what happens when you click the advanced search button in this specific visual layout? Answer, it does not refilter the page. It opens a complex overlay menu with these specific elements.
So it writes its own textbook.
Basically, this generated data is then used to actually update the model's underlying mathematical weights through a process called fine-tuning.
Wow. So it fundamentally rewires its own neural pathways based on its own mistakes, so it statistically won't make that same bad guess next time.
Right.
It's autonomously patching the holes in its own knowledge base without a human ever having to write a line of code or provide a demonstration.
It is self-improvement through deliberate self-confrontation.
Okay, so it can learn to master the quirks of a single web page by trial and error. But clicking around one page isn't navigating the internet. I would imagine if it's just trying things it doesn't know, it could easily get trapped in a local loop.
What do you mean?
Like you could just click a dark mode toggle back and forth forever because it's technically causing a visual change every time. How does it actually build a map to prevent that?
Right. The researchers anticipated that exact risk. To solve it, they introduced a higher-level navigational strategy called scale hop. Yeah. If scale is the tactical engine learning how individual buttons work, scale hop is the global strategist. It builds a massive directed graph of the AI's exploration history.
And a directed graph basically being a web of connected dots, where each dot is a unique web page and the lines connecting them are the clicks used to travel between them.
Precisely. Each node represents a specific state of the website, but defining what constitutes a new state is actually really tricky.
That was a technical detail that confused me initially. How does the AI know it has landed on a completely new page if the web address up top doesn't change?
Right, URL changes aren't always reliable anymore.
Yeah, on modern single-page applications, you can open a massive side menu or a pop-up cart, and the screen looks entirely different, but the URL stays exactly the same. How does the internal map not get scrambled?
It all comes back to the visual-first approach. The system uses a metric called the Structural Similarity Index, or SSIM.
Okay, SSIM.
Right, and it doesn't just look at the URL, it mathematically compares the structural pixel layout of the current screen to the previous one.
So it's looking at the big picture layout.
Yes. It ignores minor dynamic elements, like a flashing ad banner or a ticking clock, and focuses on the core layout. If the SSIM score drops below a specific threshold, the system realizes that the environment has fundamentally changed.
even if the URL is identical.
Even if the URL is identical, it drops a new node on its internal map.
So it has this beautifully accurate, visually driven map. But how does it decide where to go next?
It uses a mechanism called verification-guided backtracking. The map isn't just a passive record, it's an active checklist. Every node on the graph is marked with a status: unexplored, partially explored, or fully explored.
I assume it has to prove it cleared an area before moving on. Like, it probably takes a random sample of actions on the page, guesses the outcomes, and if the predictor gets them all right, it considers the node fully explored.
That is exactly how the verification phase works. Once the AI can accurately predict the outcome of actions on a page, it concludes there are no more cognitive boundaries to discover there. It marks the node as fully explored.
Makes sense.
And then, crucially, it intentionally backtracks. It looks at its global map, finds a node that is still marked unexplored or partially explored, and mathematically jumps back to that state to resume hunting.
Oh, that's so cool. It's like playing a massive open-world video game.
Yeah.
Yeah, like when you walk into a new uncharted region, your map is grayed out. As you explore, the map fills in with details. But once you 100% clear that specific zone, you don't just wander around the empty landscape forever.
Right, you move on.
You pull up your world map, look for a gray, unexplored area on the other side of the continent, and you fast travel there to find new challenges.
It is a great way to visualize it. But instead of unlocking fast travel points, the AI is unlocking entirely new structural architectures of websites. Scale hop ensures the agent's exploration is logically consistent and globally aware.
So it doesn't get stuck clicking the dark mode button.
Exactly. It guarantees it systematically covers the entire web environment rather than just randomly clicking in a localized area.
Let's talk about the results, because they didn't just build this system in theory. They turned this autonomous system loose on 19 real-world complex websites and let it run. And the output of that experiment was a massive mountain of data, the Scale 20K dataset.
Because remember, every time the judger catches the predictor making a mistake, it generates high-quality training data.
And the volume is impressive. The Scale 20K dataset comprises over 15,000 single-step tasks, almost 4,000 multi-step tasks, and nearly 7,000-page comprehension question and answer pairs.
It's a huge corpus.
It built its own massive training curriculum from scratch, purely by learning from its failures. But the real proof is what happened when they used that data to train models, right?
Like, absolutely. They tested this on models like Intern VL 2.58b and Quen 2.5 VL 7b.
And for context for you listening, that 8B and 7B mean 8 billion and 7 billion parameters. These are relatively small, open-weight models that you could actually run on a high-end local machine.
Right. We aren't talking about massive, closed-source proprietary giants operating in billion-dollar server farms.
Which makes the performance leaps even more significant. When they ran Intern VL through this self-improving fine-tuning process, they saw a 231.8% improvement in its average task success rate.
It's staggering.
And the Quen model jumped by 176.3%. Those aren't just incremental bumps.
No, not at all.
Jumping over 200% means tasks it was completely failing at before, like navigating a multi-page checkout process or adjusting complex search filters, it was suddenly mastering.
What is truly remarkable is the comparison to existing methods. The paper notes that the Scale framework actually beat out agents trained on GPT-4o's expert trajectory imitation.
Wait, really? It beat GPT-4o trajectories?
Yes, an 8 billion parameter model, armed with data it generated from its own failures, outperformed an agent trained to perfectly mimic the human-like navigation of one of the most advanced models in the world.
That is wild. Learning how to recover from your own mistakes is actually mathematically more effective than memorizing someone else's perfect run.
It seems to be. Furthermore, they tested the transferability of this knowledge.
Okay, meaning what?
Well, in machine learning, we often suffer from overfitting, where a data set generated by Model A is only useful for Model A. But they took a completely unrelated model, Alave NexT8b, which had nothing to do with generating the data, and fine-tuned it using the Scale 20K dataset.
And did it work?
Immediately, its capabilities improved. This proves the data generated by this adversarial process contains universal logic and reasoning about how the web actually works. It is essentially a digitized masterclass on web navigation.
Created entirely by an AI playing devil's advocate with itself.
Exactly.
Which brings us back to you, listening right now, and why this matters for your daily life. We are standing at the edge of a major transition. We're moving away from fragile AI that requires constant human hand-holding.
We are moving toward robust, self-sufficient agents capable of handling the chaotic, unpredictable, real-world internet on your behalf.
So when you ask your digital assistant to order those groceries, and the store has completely redesigned their website overnight, the AI won't freeze.
No, it won't care that the code changed.
Right. It will look at the new visual layout, rapidly and autonomously explore the changes, test its assumptions, correct its own misunderstandings in real time, and just get your shopping done.
It's going to save you immense amounts of time because it finally possesses the architecture to actually adapt.
It's honestly incredibly exciting.
It is. And if we extrapolate this architecture out, it raises an important question for you to ponder.
Well, let's hear it.
Right now, we are using this adversarial self-correcting loop to navigate shopping menus and click buttons. But if an AI can use distinct internal roles to actively seek out its own blind spots, challenge its own hypotheses, and self-correct on the web, what happens when this self-doubt architecture is applied to highly complex fields like medical diagnosis or advanced financial planning? Are we witnessing the early technological building blocks of artificial self-awareness?
That is a fascinating and honestly profound place to leave it. Thank you so much for joining us on this deep dive. Keep questioning the boundaries of what you know. And remember, the next time your digital assistant flawlessly executes a task after a massive site update, there might just be a tiny invisible scientist and an overconfident intern arguing inside its code to make it happen. See you next time.